Okay, so yeah, let's start. The first speaker is title is a field trial of a digital twin for the monitoring and control of a UAV swarm for wildfire detection. So please start your talk.
Thank you. So yeah, sorry for all the technical difficulties. I think now we can make a start. So I'm Georgios, and I'm presenting the work that we have done over in March with some field trials. On the right, these are a few of our industrial partners, Distributed Avionics, Wind Races, and I'm part of the University of Bristol and under Sabine's Howard's lab. So a bit of an introduction. I think everyone's aware how amazingly difficult the problem of wildfires is globally. We face very unprecedented phenomena, especially due to climate change. And wildfires is not something that's very new, but we do need to develop new technologies in order to be able to tackle this challenge. And swarms can potentially help us in that. So we also need some tools for deployment in order to do so, because it's very difficult, as everyone's aware, to interact with these systems and understand how they operate, especially in field trials. So we think that a tool that can probably work in this scenario is digital twins. So in case of you who don't know sort of like the terminology or what the digital twin is, it's sort of like a model that interacts with like real sort of like entities. So it's kind of like mirroring what happens in the real world. And we think that digital twins can help to reduce the complexity of the whole sort of trials in terms of like how the user can interact with a swarm and how we can sort of like test and optimize the controllers in real time and deploy it into our swarm. So it's a bit of our system architecture. I'm not going to dive too much in the detail of how this works, but you can see that we have a cloud infrastructure that passes all the data from the real aircraft to the digital twin and vice versa. And we also have some UIs that the operators are working on. These are a few of our control algorithms that work in order to distribute our swarm over an area and to explore that area for wildfires that might be present in that sort of like area. So in our field trials, we use these UAVs called Believer aircraft. There are 3 aircraft, and they're sort of like customized into the software that we have. I can provide some more details later on in the post session if you would like. And these are some footage from our field trials. You can see a lot of thinking going on over here on the left. But overall, we've managed to sort of like deploy them into the field with quite severe conditions as well, like I think 19 to 20 meters per second wind gusts too. So I can relate sort of like to the previous problems that we saw in the previous presentation too. Oh, time for a video. Let's see. Okay, so here we go. We can see like 2 of the aircraft flying over there, and they're sort of like loitering, and then they're sort of like tasked by the operator to change their course and change their behavior. So you can see the other one over there. And going back into our field trials, I'm going to talk about this like briefly later on, but a few of our results over here, we managed to optimize our algorithms, Wilson trials, and deploy these aircraft. We've managed to control 6 mixed reality aircrafts, some issues with 4G communication, and we're doing now 24-hour trials. And a bit of our future work, we're going to be working on digital twins and trying to assess how this work is interacting with the firefighters. And we're going to be doing some more communication, sort of like decentralized controllers in the end to react to this environment of unreliable communications. So yeah, thank you very much.
Thank you for your talk. So the second speaker, could you prepare your talk? And as he said, during the lunch session, we have a poster. So please, if anyone is interested in his work, please go to the poster session. So, okay, so your screen, your slide can be shared from us. So please start anytime, anytime when you are ready.
You see my screen, is that correct?
Yes, no problem. We can hear your voice too.
Thank you. So let me take you into the undergrounds of the Northern California Lava Beds National Monument to present to you our work on the human autonomy teaming for supervised scientific exploration, where we did a pilot study in the wild. We do real-time operations and focus on human autonomy teaming. We have a fixed base station set up at the beginning of the caves that we're exploring, and we deploy multiple autonomous robots. The goal is to do scientific exploration, to map out caves and identify areas of interest, especially for biological life. The caves itself are challenging remote environments, lava tubes in our case here. They are GPS denied and communications denied. So this comes, of course, from the underground nature of those caves. What we do is we ask a couple of questions. Which level of autonomy leads to better performance? What kind of interface requires less workload? And we vary between waypoint control as well as fully autonomous exploration, in which an operator can still intervene. And we test virtual reality interfaces and screen-based interfaces. And the real-world challenges and limitations we faced among logistical and human safety or risk of failure of robots, the most prominent ones are shared experimental time and resources, the small number of participants that one can have in such real-world scenario, and the funding, which is not unlimited, unfortunately. Our VR operations render out a real-time point cloud in which the operator can walk around, and we have a static representation of what the operator sees here, because otherwise everybody would suffer from motion sickness right now. The other modality of on-screen operations is shown here. It's a traditional 2D on-screen interface and inspired by gaming interfaces. Preliminary results suggest that fully autonomous control results in less workload, and the VR experience seems to be a bit more demanding than screen operations. To further validate our study, which is very limited with only 3 participants in the field, we are currently conducting experiments where we have the same autonomy pipeline, but replace the inputs with simulations. Everything else stays the same. And we further collect heart rate variability as objective measurement. We have extended our questionnaires for subjective measurements and collect several performance metrics. And with that, I'd like to thank our team and will welcome you to the poster presentation later. Thank you very much.
So thank you for your talk. So we will prepare for the third presenters. So if you are ready, please start. And the fourth presenter will attend our workshop in remote. Are you here? So, Dr. Dimitrov? Oh, okay. So yes. So third person. So you can start your presentation in any time. So
okay.
Yeah.
All right. Hi, everyone. My name is Marihan, and I'm a PhD student in the University of Bristol, supervised by Sabine Howard. And today I want to present to you our platform Mosaics, which is made of a swarm of robot tiles that are designed for multi-human swarm interaction for social applications, which is a novel application that has not been widely researched in swarm robotics. The platform is completely decentralized and scalable to large numbers. And we've already used it in real-world applications with more than 400 people using our swarm. And I'm going to demonstrate some of these applications now. So the first one is decision making, where we took a swarm of 30 robots to a shopping mall in Bristol, and we asked people to enter their opinion on climate change. So we asked them, what is the most important thing to do to battle climate change in your opinion? And once they entered their opinion showed on the screen for other people to see. And so the robots moved randomly in the arena, showing different opinions. And we have proved before that people seeing other people's opinions actually encourages them to enter their own opinion and voice their own opinion. The second application was collaborative art. So we gave access to people online during the pandemic to move robots around an arena, change the color of the screen as well to create collaborative art. So this is like strangers on the internet, all moving the robots around to create art together. And some really interesting art emerged, such as a palm tree over here and a football player here. And they also chased each other around the arena. It was fun. The third one is an educational application. So we took a swarm of 9 robots to school children, and we asked them to stop the robots. They were moving randomly in an arena, and also organize them as if it's a puzzle to show the Morse Perseverance robot. And then this gave us the opportunity to then talk to them about STEM careers and swarm robotics and space robotics in an interesting application. The final application is brainstorming. So we took a swarm of 63 robots to a science museum where they were interested to know what people's thoughts are about how Bristol could provide a healthier lifestyle for them. And imagine if you're brainstorming in a team, you write, 50, 60 post-it notes, but then it's really hard to go through them because there are a lot. And the idea here is that the robots would aggregate based on different themes. So it's gonna be easier for you to go through the ideas. And then the video here shows some of the robots that have ideas on them. The screen is just not, the screens of the robots are not showing due to lighting and angle, but they have ideas on them. And then they autonomously aggregate based on different themes. And this is completely decentralized, so the robots could, that just could aggregate on their own. So yes, in conclusion, we've built in Mosaics a swarm of robot tiles for social applications, which is a novel application for swarms. If you're interested, please come and visit my poster. Thank you.
Thank you for your interesting talk. And we'll move to the fourth speaker. The title of the next speech is the TRI card, enabling human-centered and rapid design of shared control in ADAS. So when you whenever you're ready, you can start your presentation.
Okay. All right. Thank you. Hi, I'm Paul Drews. I'm here presenting some work from my collaborators, Velen and Thomas, and some other folks at TRI on the TRI cart platform and an initial demonstration that we've done with it. So to summarize, fully autonomous vehicles have not arrived as fast as people thought they would. There are a lot of edge cases, a lot of challenges to making these actually work on the road, but there are a lot of novel ADAS features that are coming to market sooner than people realize. So things like automated braking, lane keep assist, advanced cruise control. There are a lot of different examples, and these are coming to market much faster than full autonomy. But testing the interaction between all of these features and the human behind the wheel is a difficult problem. It's not easy to do on a full-size vehicle. So our proposal is to use subscale vehicles, in our case, a 10-scale vehicle, to rapidly iterate on designs, prototypes, and how they interact with the human in a small controlled setting. So to that end, we built the TRI cart platform. It's based around the F1/10th platform. So a 10th-scale RC car has a NVIDIA Jetson NX on board. And we've modified it to operate reliably at low speeds so that we can easily imitate the timescales that people interact with full-size vehicles. And we also have stereo cameras and several other sensors on board. We've built a teleoperation bench. This allows us to stream video back in real time and allows an operator to control with a normal steering wheel and pedals the RC car. We get low latency control, and an operator gets an interface that they're used to. So our test scenario that we're beginning experimentation with is a merge assist. So we have the human operator on the right in yellow, and 2 autonomous drone vehicles on the left, keeping a fixed distance between them. The human's goal is to merge in between or behind these 2 vehicles. And we proposed a simple indirect shared control method that gives you visual cues based on an NPC trajectory that we calculate to merge in between the vehicles or behind the vehicles. So an example of what this looks like, You can see on the left, a top-down view of where all the vehicles are. On the right, this is the first-person view that the operator would get. There is a stop triangle, meaning that the NPC does not think that there's room to merge. If you move forward a little bit, the NPC thinks that there is room to merge. Once the operator starts moving, they'll have room to merge into the gap and be safe. And again, here they're following too close. This is slow down and speed back up. So thank you very much for your time, and come check out our poster. I appreciate it.
Thank you for your talk. So let's move to the fifth speaker. The title of the fifth speech is entitled Data Efficient Collaborative Decentralized Thermal Inertial Odometry. So you can start your speech whenever you're ready.
I'm sharing the screen. Am I sharing? Here.
Written in Japanese, so
Yeah, no. I share. Okay.
yeah, then you can start your
Perfect. Thank you so much. So, hello everyone. Thank you for coming. It's a pleasure for me to. Wait. Better. Hello everyone. Thank you for coming. It's a pleasure for me to talk about this paper here today. So in this work, we extended the JPL XVIO, a state-of-the-art thermal inertial odometry framework. We made XVIO capable of exchanging information and fusing them together to improve the state estimate of each agent in the system. So when you deploy swarm of drones, in this case, another planet, and you have like 20 minutes delay of communication, actually human interaction is quite limited. So you need to rely on actually a reliable system. So this is why we opt for decentralized system that actually makes the entire approach robust, because not relying on a central unit that actually could potentially fail and validating the entire framework. Yeah, this is actually the point that make the system robust. Also, the centralized system are scalable and requires low memory and processing power. So we opt for thermal cameras because recent advances in these sensors made them cheaper, let's say, and more accessible. And also thermal cameras allows the agents to fly in all types of light condition without the need for an external lighting source. As you can see here, we are tracking much more features in the thermal data than in the visual data in a low light scenario. This is how we extended the XVIO architecture. We made XVIO actually capable of exchanging information with other agents and then fuse the information received together. We are going to talk about each of these new blocks, starting from the front end and the feature matching. We use an online photometric calibration algorithm to attenuate the disturbances and artifacts that thermal cameras are affected by. In this way, we can track actually 4 times more tracks than in the raw thermal data, and this helps us in actually having much more collaborative updates. Then we generate VLAN descriptors out of the points tracked by the front end, and we send these descriptors to all the other agents using the IROS streaming messaging system. We built an efficient and scalable communication pipeline that sends only the VLAN to all the other robots. So in this way, the data that is going around the system is lower. And we fuse the data that we receive using the method proposed by Zhu et al. That constrain an external command filter with measurements coming from the other robots. We tested our approach on real data from the Mars UR scenario to prove that actually it works in real environments. And using the photometric calibration algorithm, the collaborative update, we actually almost halve the absolute trajectory error of our system, improving the state of the art. Our system is open source. Please try it out. And if you have questions, come to the poster presentation. Thank you.
Thank you for your great talk. So we'll go to the 5th speaker. Sorry, 6th speaker, yeah. So the 6th speaker is attending our workshop from, well, yeah, we can now see your screen. Could you speak?
Yes, can you hear me now?
Could you speak again? Could you
Yeah.
speak again?
Can you hear me?
Oh, yes, no problem. Okay, so you can start your presentation whenever you're ready.
Hi everyone, I'm Vivek Malampati, and today I'm here to talk about my work on learning trade preferences for task allocation. We see an increase in the multi-agent systems all around us. From army to the factory floors, we see heterogeneous robot teams working with humans. But when we observe closely, the agents are allocated with preference to a few particular traits more than the others. That insight has motivated us for this work. Let's take a step back to see what has been done till now. We see that trait-based task allocation methods have proposed capability-based solutions to the MRTA problems that gives us advantage in scaling and generalizability to the new robot teams. But it assumes that all traits from demonstrations have equal importance. On the other side, from child psychology to HRI, the notion of preference is very prevalent, but these concepts are missing in MRTA. Our work is a step forward to solve both of these limitations. Our approach takes in the demonstration, extracts the inferred weights and using our weight extraction function. And then the inferred weights are used to allocate the new robot team. The idea is that the new allocation will be based on the human preferences. Our novel addition to the actual task allocation pipeline is this weight extraction function. To know this, I'll introduce you to two concepts. One is observed variance. Observed variation captures how consistently a trait is allocated to a particular task. Our insight here is that the importance of a trait to a task is inversely proportional to the variability in the demonstration. That means that the more consistent a trait appears, the more important it is. Studies in psychology suggest that our ability to infer preference is modulated by the diversity of options in the observations. We leverage this insight by computing the natural variation term, which captures how diverse a trait is in the original population. We take the coefficient of variations in both cases to make it scale agnostic. Now the question is, how do we combine them both? The weight extraction function is combines these two quantities such that the observed variance helps infer the importance, while natural variation modulates the strength of the importance. And the results are amazing. It results in better trait satisfaction. The mismatch error decreases, showing us that the quality of the allocations are increasing. And our weight extraction function also gives us 100% success in extracting the order of the weights. Not only numerical simulations, we have also done experiments with real world data set. We have used FIFA 2020 data set where we have modeled the positions of soccer players as the task and players to be the agents. And we have measured how accurately we're able to allocate the players to their original task. And we have seen that the learning preference also gives us better performance and resulted in 75% reduction in computational time with a mere accuracy drop of 5%. In summary, learning trait preference for task allocation is one step forward to making these allocations better and more human-like. You can find more details on the poster and in the paper. Thank you so much for your time.
Thank you for your interesting talk.